I'm going to do an example for how to solve Coulomb's law problems when you're in two dimensions. So we've seen two dimensions with vectors, with forces, with momentum, with a lot of things that we've done, projectile motion. So a lot of things we've done this year. The math isn't new. The equation's the only really thing that's different. So similar to how we did momentum in two dimensions, we're going to look at now Coulomb's law in two dimensions. And I think this is going to be very, very similar in terms of the mathematical addition of vectors. So you'll see I make an XY chart. I'll give you the steps to solve, and then I'll do the example. So again, the math's not new, the concept's not new, it's just how we're now applying it to electric force instead of something else that we've already done. In order to solve these two-dimensional Coulomb's law problems, the first thing you need to do is list all of your given and find, including what each charge is and the distance between each and every charge. So some of them you might have to imply. It might not give you every single distance, but just doing a little bit of geometry, you'll be able to figure out all of your distances. The second thing you want to do is draw the the direction of each force on each charge. So you want to make your arrow length proportional, longer arrows for the charges that are closer together, shorter arrows for the charges that are farther apart, and you need to make sure that the direction is correct. So if it's a negative and a positive, they're attracted to each other. If it's negative, negative, or positive, positive, then they're repelling each other. So the arrows are directly related to the location of the charges and the type of charge, positive or negative. Third thing you want to do is solve for each individual force on a charge. That's going to be easier in the long run, especially if you've got a whole bunch of them. But if you're looking for like the force between charge 1 and 2, force between 2 and 3, solve them all in the beginning, and then you can just use them for later parts of the problem. Next thing, break the forces apart into their components. So this is what's very similar to vector addition mathematically. You're going to have an x and y chart. You're going to get the x component using the cosines, the y component using the sines, and then add up all your components in number 5 to determine the resultant force, which is your net force, and then the direction. So this is where you're going to do the Pythagorean theorem and then use tangent to find the angle. So I'm going to go through an example. I'll do each of the 3 charges. If you feel okay after the first one, then you're good. You don't have to keep watching to find it. The next one. Okay. Find the net force on each of the 3 charges. And the picture that it gave us, we've got a 4 Coulomb charge I labeled as charge 1. It's 2 meters apart from a negative 3 Coulomb charge, which I labeled charge 2, which is 2 meters away from a negative 4 Coulomb charge, which I labeled charge 3. Let's list our given and find. So just from the diagram, what we know. We know that Q1 is equal to positive 4 coulombs. Q2 is negative 3 coulombs. And Q3 is negative 4 coulombs. The distance between charge 1 and 2, I'm just going to call that R12, is 2 meters. The distance between charge 2 and 3 is 2 meters. We also need the distance between charge 1 and 3. So this is R13. How do we find that? Well, the charges make a triangle. So 2 meters, 2 meters, hypotenuse. These are both 45-degree angles because of the equal sides. So Pythagorean theorem, x squared plus y squared equals r squared. So 2 squared plus 2 squared, square root of 8 is 2.8, keeps on going, meters. So R13 equals 2.8, keeps on going, meters. And again, this is a triangle. So this, where am I going? 45-degree angle, and this is also a 45-degree angle. That was 90. Given all of that, it wants to know the net force on each of the 3 charges. So I'm looking for the net electric force on 1, the net electric force on 2, and the net electric force on 3. Because we're given the charges and the distance between each of the charges for all 3 of them, we can easily find the force between each charge. But when I'm solving for the net force, it's the force from 2 on 1 and the force from 3 on 1. And this one has two forces and this one has two forces. So we're going to have to add these forces together. So that's what it means when it says net force, and that's why I'm just writing total electric force on 1, 2, and 3. Okay. Beginning with charge 1. Charge 1 is positive. To the right, it's got a negative charge 2. So the force between 1 and 2 will point to the right because it's attracted. Diagonal down is charge 3. This would be Fe13. Again, it's attracted because positive is attracted to negative. This is a 45-degree angle. And we know that because, again, isosceles triangle, so 2 equal sides means 2 equal angles. So it's a 45-degree angle that Fe between 1 and 3 is directed. So let's solve for each of these forces. Fe12, K, Q1, Q2 over R squared. So K, Q1 is 4 coulombs. Q2 is 3 coulombs. And we're just looking at the magnitudes here. Divided by 2 meters squared. This comes out to an even 2.7 times 10 to the 10th newtons, and it's directed right. So it's positive. Fe13 equals K Q1 Q3 over R squared. This is R13. This should have been R12. So K, 4 coulombs times 4 coulombs over my unrounded 2.8 keeps on going meters squared equals 1.8 times 10 to the 10th newtons. And this direction is 45 degrees. And looking at the components, it goes down, so that's south, and it goes right, so that's east. South of east. So I know what each force is. So the force between 1 and 2, the force between 1 and 3. My total electrical force on 1 equals Fe12 plus Fe13. I can't just straight out add them though because of this angle here. So because this has both x and y with that south and the east, we need to break it apart into the x and y components. Okay, making our xy chart. Now to add these vectors. Looking at Fe12. It has an x component of, separate this off, 2.7 times 10 to the 10th newtons. There's nothing in the y. This is positive because it's pointing to the right. Fe13, your x component, so Fe13x equals Fe13 cosine theta. Fe13y equals Fe13 sine theta. So just like you would find an x and y component for anything else we've done this year, forces, vectors, momentum, you're breaking it apart. X uses cosine, y uses sine. So Fe13 will equal 1.8 times 10 to the 10th newtons, cosine 45 degrees, and the y component 1.8 times 10 to the 10th newtons, sine of 45 degrees. And the most important thing to remember here, remember this went Fe13 was 45 degrees south of east. So south means that this y component is negative. You can't forget the negative, it'll mess you up. So adding our two components, we get negative when we multiply this out. 1.27 keeps on going, times 10 to the 10th newtons. Adding the two x components together, 3.97 times 10 to the 10th newtons. So we have our x component and our y component. Now we need to do the trig. X component is positive, Y component is negative. So this is the 3.9 times 10 to the 10th newtons. This is the 1.27 times 10 to the 10th newtons. My resultant force, right here, this would be the total net force on 1. So just doing Pythagorean theorem, x squared plus y squared, square root of those, we get Fe1 equaling 4.17, keeps on going, times 10 to the 10th newtons. Then we need to figure out the angle. For the angle, I always like to use inverse tan of the y component over the x component. So this would be 1.2 times 10 to the 10th newtons over 3.9 times 10 to the 10th newtons. Angle equals 17.76, keeps on going degrees. And this is the theta we're referring to. So because it points right, that would be east, and down, that would be south. My total net force with sig figs is approximately 4 times 10 to the 10th newtons at 20 degrees south of east. Yes, all of these fun vectors with directions came back. If you felt okay with this, then stop watching. We'll do more practice with this tomorrow. If you want to see the rest of it, so I'll solve for charge 2 and charge 3, then keep watching. Now let's move on to charge 2. Charge 2 is negative. It's got a positive charge to the left, so it's going to be attracted. So this would be the electric force between 1 and 2. And it's got a negative charge going straight down. So, like charges repel, so this is the force between 2 and 3. We already know that Fe between 1 and 2, we solved that for charge 1, is 2.7 times 10 to the 10th newtons, and that was directly right. In this case, it's left. And I know that just by looking at the picture. So because it's left, this is negative. Let's solve for the electric force between 2 and 3. K, Q2, Q3 over R, 2, 3 squared. K, my Q2 is 3 coulombs. My Q3 is 4 coulombs over 2 meters squared. This equals 2.7 times 10 to the 10th newtons. This points up, so it's positive. Breaking both of these apart into their x and y components, they are both x and y components, so there's no trig here. Fe12 is only in the x direction, and it's negative. So negative 2.7 times 10 to the 10th newtons, nothing in the y. Fe23 has nothing in the x, and positive 2.7 times 10 to the 10th newtons in the y. So we get negative 2.7 times 10 to the 10th newtons, and positive 2.7 times 10 to the 10th newtons. So x and y components. My x component is negative, my y component is positive. So 2.7 times 10 to the 10th newtons, 2.7 times 10 to the 10th newtons. Here's my resultant net force on charge 2. This is easy because they're equal sides, so these are both 45-degree angles. So Fe2 equals the square root of 2.7 times 10 to the 10th newtons squared plus negative 2.7 times 10 to the 10th newtons squared. This comes out to 3.82, keeps on going, times 10 to the 10th newtons. The angle we said was easy, 45 degrees. X goes left, so that's west. Y goes up, so that's north. So this would be north of west. So my total electric net force on 2 with 1 sig fig is approximately 4 times 10 to the 10th newtons at 45 degrees north of west. So this one arguably a little bit easier to solve just because there were no angles in terms of the x and y components. Now let's look at charge 3. This will be similar to charge 1, and then we'll have solved for all 3 net forces. So charge 3. Charge 3 is negative. It's got a -2 directly above it, so the force between 2 and 3 will point down, and then it's attracted to charge 1. And this is the charge between 1 and 3, so it points in that direction. And again, we know this is a 45-degree angle because of the isosceles triangle. So we already know what Fe 1, 2 is equal to. In this case, it's 1, 3 is equal to. We solved that when we were looking at charge 1. So that's 1.8 times 10 to the 10th newtons. And this is at 45 degrees north of east. And then Fe23 is equal to 2.7 times 10 to the 10th newtons. This is going down, so that means this is negative. My XY chart, Fe13, Fe23. In the x direction, so this would be 1.8 times 10 to, this is north of west. So 1.8 times 10 to the 10th newtons. Cosine 45 degrees. This is negative because it's pointing left. So this would be the x component, this would be the y component. So you have to make that negative. And then in the y direction, 1.8 times 10 to the 10th newtons. Sine 45 degrees. This is positive because it's pointing up. My Fe23 has nothing in the x direction. In the y direction, it's going down. So this is negative 2.7 times 10 to the 10th newtons. Adding those together, we get, this is negative 1.27 times 10 to the 10th newtons. Keeps on going. And this is negative 1.43 times 10 to the 10th newtons. Both of these components are negative, so I've got a negative x component and a negative y component. This was the 1.2 times 10 to the 10th newtons, 1.4 times 10 to the 10th newtons. So here's my resultant. This is the net force on 3. So Pythagorean theorem again, I'm not going to write it out. This equals 1.91, keeps on going, times 10 to the 10th newtons. My angle, we're using inverse tan. This is the angle I want of y over x, and this comes out to 48.3, keeps on going degrees, because they're both negative. This is west, this is south, so this would be south of west. So net force on 3 with 1 sig fig is approximately 2 times 10 to the 10th newtons at 50 degrees south of west. So all we're really doing here is vector addition mathematically. It's nothing new. It's probably a little bit rusty since it's been a while that you've seen it. But again, nothing really new, just applied differently in terms of Coulomb's law.